Hi everyone, I'm Sean Koyama. I'm an HPC Systems Administration Specialist at the Argonne Leadership Computing Facility, and I'll be talking about the Aurora Programming Environment. Okay, so just a brief hardware overview of Aurora for those who aren't familiar. Aurora is one of the DOE's Exascale computers, so it has a bit over 10,000 nodes, 2 processors and 6 GPUs on each node, and it just clears the Exascale mark at just over 1.0 exaflops. It has a slingshot 11 fabric and then 3 file systems available on it. There's Deos, which is a high-performance object store, so that's more of a scratch space, not super relevant for us. There's a Lustre file system, which I'm sure you're familiar with. It's a parallel file system. And then that's for like project user storage. And then we have a NetApp NFS share, which we have the user home directories on, but we also have this directory called /soft. /soft is ubiquitous across the ALCF. Historically, it's where it's a shared file system where our facility maintained software lives. And so we still have this on Aurora, but because of the scale and some of the issues we ran into, we haven't been able to use it successfully for the type of software deployments that we're used to. So that's part of what I'll be talking about. Okay, so before I tell you what the Aurora PE is, I'm going to tell you why the Aurora PE is. We had 2 major criteria for designing our software environment on Aurora. These are scalability and maintainability. Scalability is obvious. Aurora, during its development, was pretty novel in its scale. I think it's still relatively novel in the scale. And so, loading libraries, shared libraries, or dynamic libraries off of shared file systems just doesn't work. You can't scale that out to 10,000 nodes very well. There are tools that can help, like Spindle and Copper. And those are available on Aurora, but for various reasons, they didn't meet all of our criteria. And there's also the second criteria of what we wanted to achieve with designing this environment, which was maintainability. Historically, shared software deployments have been really messy. These like ad hoc installations of 20 different staff installing all their own libraries into this shared file system. Doesn't work. Thankfully, E4S and the Spack project as a whole kind of really helps with that and unifies that into a stack. But still, if you have your software stack on a shared file system decoupled from the OS image upgrades can break things, and that decoupling can be a real issue. So we wanted to try tackling that when we were designing this. So kind of in summary, we want something that scales well and integrates with the OS environment. In practice, integrating with the OS environment means actually relying as little as possible on the OS environment. And so ideally, when we deploy these stacks, we would have version stacks that can be swapped in and out with each other as self-contained environments, hence the programming environment name. So with all this in mind, we designed sort of this rough architecture or idealized diagram of the programming environment. So on top of our base OS image, which is a SLES 15 with a bunch of kind of vendor-provided RPMs on it, stuff like libfabric, we build the OneAPI SDK and frameworks. Those are vendor-provided packages. So we won't talk about frameworks much. That's a Conda environment. But the OneAPI SDK is where the compilers come from. It's where we have a lot of high-performance libraries. And then on top of that, we use Spack to build out the entire rest of the scientific software stack. So that's like build tools, things like CMake, libraries like HDF5, whatever else you can think of, and MPI. So we have MPitch on Aurora. That used to be its own vendor-provided package, but we pushed really hard to move that, move to an open source-based build, which we now handle in Spack. So the vendor-provided parts, which are installed via RPMs, and the Spack part are packaged together into the Aurora PE. They're packaged into a squashfs, which is mounted off of an NFS share in this /opt/Aurora path. And so kind of part of the idea of this was that we could have different PE versions and different squashfs's that are all versioned, and then users or admins could mount different versions as required into different sort of subversion directories, mount points in /opt/Aurora. And that also allows us to mount multiple versions of the PE at the same time. All right, so that all sounds good, but how do we actually build this out? We landed on containers. Containers create a really reproducible and portable build environment. So the entire PE build, including the vendor-provided stack and the Spack stack, happens within a container build. And so this is because we can pull a container image and build an image that matches the actual compute node image almost exactly. And it's also amenable to CI and automation, which we're working on at the moment. And there's potential for even further kind of systems level integration, which I won't talk about too much, but we can talk after if you're curious. And then just a note that we use Builda. That's, if you don't know, it's the container build backend to Podman. So we use that to build the container. That's just sort of has to do with the history of the development of the PE. That's the tool we ended up using. It works fine. OK, so just a quick kind of summary of the Aurora PE build flow. So the build is coordinated by a parent install script. It's just a bunch of bash scripts. Even the builda commands are just build script or bash scripts running inside of a container. So we have install.sh, which starts by building a base container off of a /15 container image. We then, once we have that and kind of the basic image built up, we install the OneAPI stack, which gives us our compiler toolchain. So I just want to note, that is separate from Spack. Right? That's installed with RPMs. There's a lot of work that I'm not going to talk about today with integrating OneAPI into a Spack environment. I have a lot of thoughts about that. If you're having trouble with that, or if you have thoughts on it at all, please talk to me. But after we install the toolchain, we do the Spack PE build. And that's what I'll focus on for the rest of the talk. We also, after Spack is done, we install frameworks and then package it into the SquashFS for deployment. Ben Allen, who is on the systems team, has done a lot of clever things to make that packaging and mounting and provisioning really, really simple. So the Spack PE, it's familiar stuff. It's what the last several speakers have been talking about. Essentially, it's using Spack to build a software stack. So roughly, the steps are we copy in and generate Spack configurations. I guess the one thing that is a little different from a typical flow is that we quote unquote bootstrap a GCC installation. I'll explain what that is a little later on. And then for each OneAPI version that we want to support, we build up a Spack environment and a software stack. And finally, we do the kind of finishing touches. I'll note that these blue boxes are kind of like pain points or like issues we encounter that I just want to highlight. So I'm going to mostly focus on just kind of the key points where we either encountered major issues or had made some sort of improvements or just changes for site-specific changes to Spack or the workflow. OK, so one of the first issues we ran into is that Spack's external detection we found lacking. It first depends on the package to implement. A lot of packages don't implement external detection very well. And most packages don't actually check that a development version of the package is installed. So if you have the curl binary available, Spack might think curl is a valid external. But in order to build against libcurl, you need libcurl.so, and you need the curl headers. So we thought that wasn't very good, or at least it was inconsistent. So I wrote an extension called detect system externals. It does what it sounds like it does. Setting it up is a pain because it's a dictionary map of the keys are Spack package names, and then the values are the corresponding RPM names. And it can be one RPM or multiple that are required for it to be a real development package. So I had to make that by hand, but thankfully, and I use this on, by the way, not just Aurora, but other ALCF systems. Thankfully, most of our systems use /15, so I only had to do it once. But once you have this map made, it's a really simple script. And basically, it just goes through all of the known externals, looks for them, does an RPM query. If it matches the RPM query, then it'll configure that external in a packages.yaml format. And there's some extra options and features too, if you're curious. But this takes like 10 seconds, and it finds several dozen externals, so it's pretty efficient. Okay, so once we have all the configurations set up, I mentioned this GCC bootstrap step. It's not really a bootstrap. It's just building GCC with the system compiler, which is also GCC. The idea is that we do want to separate the PE dependencies away from the OS image dependencies as much as possible. So we build GCC, which of course provides its own like standard libraries. It comes with standard C++, for example. But we can't avoid a coupling with the OS image. I mean, we are building in a Linux environment, and of course we need some of the standard libraries. And another thing is the GCC version that we do build is chosen because there's a certain vendor software stack dependency that just constrains what we're able to do and what version of GCC we're able to build. So that coupling is sort of limited inherently by the vendor choices in the system design, but we do what we can. Okay, so we build the Spack stack like many other people do, using these spec matrices. I guess things I want to highlight here, we have a lot of specs, largely because we currently deploy 6 different MPitch builds, just the requirement from our users. So we end up with 566 specs per one API version. Thankfully, right now, we're only deploying 1. But if we deploy 2 versions, it gets kind of crazy. But we do have like different Spack environments for each one API version, so it's not too bad. And we maintain custom package repo, a few dozen packages there, and pull in external package repos from internal collaborators. Mostly, they just develop their own packages and then package it into Spack for us. Okay, this is one of the major pain points. People have brought it up before. I was really excited to hear that talk about build concurrency because these build times can be kind of a pain. So with the naive concurrency of spawning just say like 8 Spack install processes, each with -J4 or something, it takes like over 10 hours to build 1 stack. So we were looking at like 24-hour build times for when we were building 2 stacks at a time. We did implement, and we've run into kind of issues with like when we really push it to the limit, we run into like file system lock failures. We tried the dep file generation, it didn't really work for us. So it's been sort of something we've put a lot of effort into working around, and my collaborator implemented a sort of manual parallelization where he split the spec list into chunks that are then each installed 1 chunk at a time, and that's taken our build time down to 4 hours. He's convinced we can do it in less than an hour. I think that's a little ambitious, but we do think there's room for improvement there still. Ideally, we could, I would love to see a feature where we can have a build farm, building using multiple hosts. The challenge for us is that because this build happens in a container, we're not building into a shared file system. So we can't just do, split it out onto multiple hosts really easily. Another thing, though, that we haven't implemented fully yet is a build cache, so that I think will improve our build times by quite a bit. I do have like local build caches going, but as far as shared infrastructure, we still have to set that up. But I'm also open to ideas. Okay, so once we do the installation, we just do the kind of finishing touches. So one of those things is configuring packages. After the fact, someone else brought this up. It would be nice to have standard practice. The way we do it is we just have like our, for example, podman requires containers.conf in its install prefix. We just rsync it in. So we do that for a couple of packages. I'm going to skip over this. This is kind of obsolete. I wrote it 2 years ago before upstreaming worked super well. So module files is another major point where I had to kind of iterate a lot on making it work for us. I know there's a lot of like anti-module people here. Just plug your ears, look away for this part. So we do need to use module files. It's kind of non-negotiable for our facility. And something I noticed is that Spack likes generating modules for all of its specs, including externals that have their own module files. And so I wrote a patch for Spack to respect predefined external modules. So for example, if a compiler is loaded through a module, Spack will respect that. Or actually more applicable is if a certain dependency requires a module, Spack will point any dependent modules to that module instead of a Spack-generated module file. And then I wrote this extension called purge external module files, which deletes sort of the extraneous module files that get generated for mostly just system externals, stuff in /user. Those don't need module files. So it just reduces the clutter for our users. And it's a really simple extension. We do make use of an LMOD hierarchy. We do have to do custom adjustments. This is the one API module. This is not generated by Spack. So we do our own little thing to push in the Spack installation or the module file paths to make the hierarchy work when we load the one API compiler. But we also have to do some manual stuff for Spack-generated modules, specifically mpitch. So we use the automatic hierarchy generation, LMOD hierarchy generation for MPI. The issue we've run into, though, is that it only generates a hierarchy for the compiler that mpitch was compiled with. But if we have a spec that's compiled, say, with GCC that depends on mpitch compiled with one API, it won't automatically add the GCC modules, which we have it defined as core modules, into the hierarchy. So we have to manually make sure that those specs module files are part of the module hierarchy. Finally, one of the finishing touches, which doesn't really work, hence the to-do, is we copy out configuration files for users to use. And then just to show you what it looks like on the system itself, this is just on the login node, but we have a default module set. We provide a lot of GCC compiled packages, mostly like build tools, stuff like that. And then these are the hierarchical module files. And we can somewhat easily switch between PE versions. Sometimes it's a little finicky. But if we have multiple PEs mounted at once, you can just load a different one API version that corresponds to a different PE and its corresponding mpitch, and then the LMOD hierarchy will do its magic and automatically kind of sort through all that. OK, so that's the gist of the Aurora PE. There's a lot of challenges and future improvements. If you know anything about any of this stuff, please talk to me. I would love to hear from you. But yeah, with that, I'd just like to acknowledge my collaborators, Servesh and Ben, as well as Chris from Intel, and thank the E4S project, ECP, and the Spack team and community for all of your work. So thank you very much.